This is Rosen, Discrete Mathematics and its Applications, section 3.1 on algorithms. The person at the top has the name from which we derive algorithms. It's also the name from which we derive the word algebra. And I'll let you read about him in your textbook. All right, what is an algorithm? What is a finite set of instructions for solving a problem or doing a computation? We have an example here. We're going to find the maximum value in a finite sequence of integers. All right, so how might we do this? We've got to establish the steps. So we'll do that just with some English here. Well, one of the first things you might do is start at the beginning of the list and set the temporary maximum equal to the first integer on the list. So we have this idea of a temporary maximum, sort of a variable, if you will. And then we'll check the next integer and compare it to that temporary maximum. And if that next integer is larger than the temporary maximum, guess what? We found a new temporary maximum. And then we continue this until we get to the end of the list. And then we stop. Once we have stopped, that temporary maximum will be the absolute maximum for the sequence. So this is a very straightforward and simple but effective algorithm for finding a maximum on a list. All right, so the way we write down algorithms, we just saw one, is just sort of list the steps in some sort of English fashion. Another way to do it would be to write it out in what is known in the computer science world as pseudocode. Pseudocode is not actual software syntax, but it's something in between English phraseology and very exacting syntax of a programming language. For this class, we use a pseudocode described in your Appendix 3. So if you don't have very much coding experience, or you want to make sure you understand how to read our pseudocode, then please check out Appendix 3 in your textbook. It is similar to C++ and Java, but not exactly the same. And the nice thing about it is it's fairly straightforward. If you can write something down in pseudocode, it's usually less work to actually code it. But even more important, what pseudocode does is it helps us to analyze the algorithm that we have written in order to check how long it takes to solve a problem. And that helps us to do what's known as complexity analysis, which we'll learn later in this chapter. All right, some of the properties that algorithms have. First, they have to have an input. You're usually going to need some kind of data that describes the problem you're trying to solve. Earlier, it was a list of integers. The output is how you answer the solution, or you provide the solution. Earlier, our output was a maximum value for the list. Correctness. The algorithm should be structured logically so that it always produces correct values. Finiteness. You shouldn't code an algorithm that takes an infinite number of steps to solve a problem. That would not be considered an algorithm. Kind of capturing both of these is this concept of effectiveness, although it's slightly more nuanced than that. Effectiveness doesn't have to do with correctness so much as it being a reasonably time-constrained approach to the problem. It's possible to have a correct algorithm and even a finite algorithm, but it takes too long to solve the problem, and so it would not be considered a useful algorithm. And then finally, it should work for all problems of the desired form. You could imagine a simple algorithm solving a problem with very structured data, but it wouldn't work on unstructured data. So if the algorithm might encounter unstructured data, then it needs to be designed for that. All right, speaking of pseudocode, here is a pseudocode version of our search for the largest integer. We typically call our programs procedures that is going to be called in some sense by not a computer, because it's not a computer language, but that's very computer-like syntax there. And then we give it a name, and then here we designate the input in parentheses after the name. And for this one was just a list of integers. And here's our temporary variable, max, set it equal to the first integer. And then we establish a for loop that starts our index at 2 and runs it all the way to the end. And here's where we compare the next integer to our max, and if that next integer is bigger than our max, we change max to that new integer. Remember, these are the temporary maximums until we get to the very end, at which time max becomes the largest value. And so, does this have all the properties listed? Well, it does, I think. Input, the list and the length of the list. Output, the maximum at the end. Correctness appears like it would work logically. Finiteness, it'll take no longer than n loops or less n minus 1 loops to find the answer. Effectiveness, generally n steps for solving a problem size n is considered effective. Generality, no structure is assumed on this list. Typical problems that we might try to solve with algorithms. Searching problems, we just solved one where we're searching for a maximum, but we might also try to find a location as well. Sorting problems, very common in the computer science world, and also very common in the computer science and applied math worlds, are optimization, finding the best performing set of features. So let's look at another searching problem. Here we're going to try to find an element X. So here's a new input. We have our list of elements that we want to search, and then we're looking for a specific value called X. And to answer the problem is not to tell us what X is. We already know what X is. That's an input. We want to know the location of X on that list. And so the answer will be an index or a location. And if it's not on the list, we return a 0. And why might you want to check the list to see if X is in it? Well, a library would want to know whether a patron is on a list of those with overdue books. Any number of reasons you might want to check a list for a specific value. And in the next slide, we'll study linear search, and then in a separate video, we'll discuss binary search. All right, so how does linear search work? It's going to look a lot like the search for the maximum value. We're going to start with the first element in our list, and keeping in mind the value we're looking for, X, we compare to see if they're equal. If they are, we return the position 1. And if it's not there, we try A2, and if it turns out to be X is equal to A2, we return position 2. And then if we keep going, eventually we either find it or we get to the end of the list, in which case we return 0. And here is this same problem in pseudocode. We're going to call it a procedure. We're going to name it linear search. There's our value we're searching for, X. Here's our list of length n of distinct integers, we say. None are the same. That's some added structure. And instead of a for loop, we're going to use a while loop and do the checks inside the test for the while loop. We'll start with our index equal to 1, and while our index is less than or equal to n, and a sub I is not equal to x, we're just going to continue to increase that index. If we ever encounter an a sub I that's equal to x, then we break out of this while loop, and then we return location I if I is less than or equal to n. If we get all the way through all values of all elements in our list, then this last I plus 1 is going to render I greater than n, and so the location will be returned as 0. And that is the linear search algorithm in pseudocode.